Alright, in this video we cover section 2.2 on reduction of order. So in the previous section we discussed the nature of the solutions of differential equations of higher order, that is degree 2, 3, etc. or higher order, but more like the theory behind the solutions and their linear independence. Okay. However, before getting into the methods of solutions to those higher order differential equations, we need one more piece of information, one very powerful tool that will help us have a better understanding of how the subsequent methods work. Okay, so we're going to talk reduction of order. So we're going to solve second order differential equations by reduction of order. So, well, consider the equation y double prime plus p of x, some function of x, y prime, plus some q of x, which is again a function of x, just like p of x, multiplying y to the first power. Again, from day one of class, consider this as a linear differential equation in y because all of the y's or their derivatives are just raised to the first power, or also the functions that multiply those y's and y when in their derivatives do not depend on y. Okay, so and it's also homogeneous because it's set equal to 0. So we're going to start with the idea that one solution is known, will be given, okay, that is y sub 1, or could be guessed, okay, but for the most part will be given. All right, well, it is possible to know a second solution using this formula right here, which before getting into the exercise, I'm going to derive this formula. All right, so to prove this result, well, we're going to start with the fact that y sub 1 is a solution to the differential equation. That means that if you substitute y sub 1 into the differential equation, okay, so this has to be a solution by hypothesis. Well, it has to give you a 0 on the just like the right hand side. Okay, so that means y sub 1 double prime plus p of x y sub 1 prime plus q of x y prime equals to 0. So now let's consider a second solution. So a second solution of the form y sub 2 equals to Vy sub 1. All right, now from this moment and on, actually, I'm going to omit the parentheses x just to be more compact with the notation. But keep in mind that all these y's and v's are functions of x. So really, this expression here is the same as saying y sub 2 of x equals to some function v of x times y1 of x. And that's just, again, to be more compact with the notation. Okay, so since we are looking for a second solution, and we're going to set up a solution of this form, that is y sub 2 equals some function times y1. Okay, let's assume that's the form of the solution. Now again, because y sub 2 is claimed to be a solution, okay, y sub 2 is a solution, then it will satisfy the differential equation. Substitute into the differential equation, and of course it's going to give you 0 equals 0. Okay, well, we're going to take the first two derivatives of this solution. Okay, so number one, so because this is a product between two functions of x, we will use the product rule, and recall that the product rule uv prime equals u prime v plus v prime u. That is, in this case, v prime y1 plus y prime times v. Okay, we're also going to take the second derivative. Okay, so actually I didn't write the second derivative. I think I'd rather write it down. All right, okay, so the derivative in this case up to product, and let me differentiate the first product, the one I circled. So that'll be v double prime y1 plus y1 prime times v prime. Okay, so that's done. Let's differentiate the boxed product. So the derivative of y1 prime, that'll be plus y1 double prime v plus v prime y1 prime. Okay, well, notice in this case there are like terms that I would like to combine. Actually, the v1, the y1 prime v1, and then y1 prime v prime was as well. So we're going to end up with v double prime y sub 1 plus 2 v prime v prime y sub 1 prime plus y double prime sub 1 v. Okay, all right, so what we're gonna do is we will substitute. Okay, let me go back to the equation. Okay, let me actually do some highlighting here. Okay, so we use a different color for this. So we use yellow for y. We're gonna substitute that here, and then use red for the first derivative, which is going to be substituted here. And lastly, I'm going to use another color here, maybe like brown. All right, so the second derivative, which will be substituted here. All right, so some substitutions, we're going to end up with a big expression. Okay, so this will be v double prime y sub 1 plus 2 v prime y sub 1 prime plus y sub 1 double prime v. Okay, so that's the second derivative term. Okay, plus p. Okay, notice again the original equation says p of x, but again these are functions that depend only on x. I'm just gonna write the letter p to avoid having too many parentheses. Okay, and then I'm gonna multiply by the quantity highlighted with pink, that is this first derivative, which is v prime y sub 1 plus y sub 1 prime v. Okay, and plus q times y, which is the proposed solution, v times y sub 1, and that equals to 0. Okay, what we're going to do here, I'm going to distribute the p. I'm going to distribute p over these two terms. Okay, that's going to leave us with the following. That is, okay, the first three terms remain the same. V double prime y sub 1 plus 2 v prime y sub 1 prime plus y sub 1 double prime v plus p v prime y sub 1 plus p y sub 1 prime v plus, in this case there's nothing to distribute, just multiply across, q v y sub 1, just y sub 1, and let that be equal to 0. Okay, what are we going to do here at these steps? Because, well, we have like a bunch of terms like all over the place. Well, the trick here is to let me highlight all terms containing the v. Okay, let's highlight all containing v. That is this one right here. Let me use a different color so it doesn't get confused with other highlightings here. Okay, highlight all terms containing v, not v prime, not v double, no, just v. Okay, v to the just single v. Okay, and I'm going to put them together. Okay, I'm going to put these three terms together, and at the same time I'm going to factor them out of the three terms. So that's going to give us v, okay, times, factoring the v out of these three terms, that'll be y double prime sub 1 plus p y sub 1 prime plus q sub q times y sub 1. Okay, well, then let me just rewrite everything else we're left with. That is plus v double prime y sub 1 plus 2 v prime y sub 1 prime plus p v prime y sub 1, and I believe that's it. Okay, that's about it. And let's keep writing everything equal to 0. Now, why did we factor the v out of these three? Because, okay, what do you think about this? So check. By hypothesis, y sub 1 is a solution to the differential equation, right? So this means that because it satisfies the differential equation, that equals to 0. So all this right here equals to 0. Okay, this will leave us with the following. Okay, well, this is equal to 0 or because of. Actually, I should have labeled this as 1 and label this as 2, and that because of 1. Okay, all right, well, so that leaves us with the following: v double prime y sub 1 plus 2 times v prime y sub 1 prime plus p v prime y sub 1 equals to 0. What are we going to do with this? Well, that's still a second order differential equation. Well, here is the part where we will reduce the order of the differential equation by performing the following substitutions. That is, whatever you see, okay, whatever you see later, the v prime, so v prime will be replaced with a u, and on the other hand, v double prime will be replaced with a u prime. All right, so that's how we reduce the order. So a second order differential equation will be reduced into a first order differential equation. Well, so this becomes u prime, okay, the substitution u prime y sub 1 plus 2 v prime, which is u, y sub 1 1 plus p times v prime, which again is u, y sub 1 equals to 0. Okay, well, guess what? This differential equation is the same as saying, well, actually, before doing anything, okay, this will be some du dx. Well, again, keep in mind everything is dx here, all right? Only this guy right here, okay, the u prime. Now, what I'm going to do next is move the other two terms to the right hand side, factor it out, and divide out to solve a separable equation. So a second order differential equation becomes a first order differential equation by doing a couple of substitutions, which at the same time becomes separable equations, which will make the problem even easier to solve. Okay, so that's going to be okay. Let me change the derivative symbol, du dx times y sub 1, and let me let this equal to, okay, this is negative 2u y sub 1 prime plus minus p u y sub 1, and let me factor out u. That'll be actually, I'm going to factor negative u, not just u. Let me factor negative u. Okay, and that's going to leave us with 2y1 prime plus p y sub 1, and that equals y sub 1 du dx. Okay, let me, okay, I'm going to add another page. Okay, let me add another page. And let me continue with the derivation here. Okay, so let's actually separate the variables. Okay, coming back to the differential equation here, I'm going to divide both sides. Okay, I'm going to divide both sides by u y sub 1. U y sub 1. Here to cancel the u and here to cancel the y prime. Okay, so also I'm going to multiply both sides. Okay, let me do everything in one shot. I'm going to multiply both sides by dx to cancel the dx on the left hand side. All right, okay, so let me go to the back side of the page here. That's going to leave us with the following: du over u equals negative 2y1 prime plus p y sub 1, everything divided by y sub 1, that times dx. Okay, well, what do we have on the right hand side of the equation? Well, let me keep this du over u, and that equals, okay, let me split the fraction. Actually, let me split it like negative 2 y sub 1 prime over y1 plus, okay, there's still parentheses here, okay, put parentheses not brackets, and the y1's canceled, and that's simply plus p dx. Okay, well, actually at this point we may go ahead and integrate both sides. That's separable equation. Du over u, this is equal to e to the, oh wait, not e, it is equal ln of u. Okay, actually technically I should put absolute value bars. However, I'm going to skip them for now. I'm going to skip these absolute values. I'm going to omit them, and I'm just going to integrate these two. Let me actually separate this into two integrals. This is minus 2 times the integral of y sub 1 prime over y sub 1 dx minus the integral of p dx. Okay, well, the integral of p dx, well, we cannot evaluate it because we don't know what p is right now, all right? However, I think you might remember seeing this integral in that humongous formula. So, okay, and well, here we can integrate this because, okay, because we have y sub 1 prime in the numerator of y sub 1, so this is actually going to call the ln rule just like we did here. So this is ln of u equals to negative 2 ln of, what is that? Ln of y sub 1 minus the integral of p dx. Okay. So now, well, we want to solve for u. Let's exponentiate both sides on the base e. Okay. And that'll give us u, because we can cancel e with ln. So u equals to e to the negative 2 ln of y sub 1 times e to the negative integral of p dx. And yes, you might be thinking of canceling e with ln, but we can't, so that's because of the coefficient negative 2, so make sure to basketball it first. Okay, have the coefficient be the exponent of the argument by one of the properties of logarithms, and that'll be u equals to e to the ln of y sub 1 to the negative 2. And well, this is times still e to the negative integral of p dx, okay? All right, well, so at this point, we may cancel out e with ln, and u equals to y sub 1 to the negative 2 times e to the negative integral of p dx. Okay, well, we are almost done. Well, a couple more steps. Well, there's a couple things I'd like to do. So number one, because I don't want u, actually we're gonna back substitute for u in terms of what we did before. So u was that v prime. Okay, it's right here. Okay, let me go back. So, but u equals v prime, which at the same time v prime, I'm going to write it as dv dx. Okay, so u, oh no, not u, that's dv dx equals to e to the negative integral of p dx. All I'm going to do right here, I'm going to send the y to the negative 2, y sub 1 to the negative 2 to the denominator with positive exponent. And then I'm going to multiply both sides by dx dx to separate the variables. All right, so cancel, and dv equals to e to the negative integral of p dx over y sub 1 squared dx, and we may now go ahead and integrate both sides. Okay, so let's integrate dv. Well, the integral of dv will simply be v. Okay, v equals the integral of e to the negative integral of p dx, everything divided by y sub 1 squared dx. All right, well, so we have a solution for v, but again, we're not looking for v. we're looking for y sub 2. So again, let's go back, okay? Let's go back to our first substitution. Well, again, keep in mind that v is related to y sub 2 by being multiplied by y sub 1, okay? And we're almost there, actually. Okay, let me continue with the derivation here, okay? Okay, another... Okay, so another... But y sub 2 equals v times y sub 1, which at the same time solving for v, that equals y sub 2 over y sub 1. All right, so that's what I'm going to substitute here. Okay, so y sub 2 equals, y sub 2 over y sub 1 equals big integral of e to the negative integral of p dx divided by y sub 1 squared dx. And well, to solve for y sub 2, just multiply both sides by y sub 1, and y sub 2 equals big integral of e to the negative integral of p dx, everything divided by y sub 1 squared dx. And that times, oh, I forgot to multiply y sub 1 here. All right, and that's actually the end of the proof derivation. So that's the formula we're going to use. The reduction of order formula to solve second order differential equations when you are when you're given one of the solutions. All right, I know this derivation proof, it's kind of lengthy, but it's an important one. We need to understand where it's coming from, how it is related to the corresponding substitutions, because this is a very important tool for the subsequent sections. Okay, all right, well, how about we look at the examples? And guys, the examples are going to be very formulaic: identify, substitute, evaluate, simplify, final answer. All right, so example number 1. So we have that the function y sub 1 equals to x squared is a solution to this differential equation. They're asking us to find the general solution of the differential equation. Okay, now you guys need to be very, very careful when working with these equations, because the given equation here is not given in the format we required in order to solve it, because you want to make sure that the second derivative term has a coefficient of 1. All right, nothing is multiplying the second derivative term other than 1. And in this case, we have an x squared. All right. Okay, so this is y double prime equals to 3 minus, oh, not equal, minus 3x over x squared, which is 3 over x. Okay, y prime plus 4 over x squared y, and let that be equal to 0, because 0 over x squared is still 0. All right, so from here there are two pieces of information that we care. Number 1, well, y sub 1, which is given, and whatever multiplies our first derivative term, that'll be our p of x. Okay, p of x equals to negative 3 over x. Okay, so the rest of the problem is just substitute into the formula, that is, find the second solution, y sub 2, by evaluating this humongous integral, that is y sub 1 times the integral of e to the negative integral of p dx divided by y sub 2 squared dx. Okay, all right, so this means y sub 1, which is x squared, times the integral of e to the negative integral of negative 3 over x dx, everything divided by y sub 2. No, actually this is y sub 1, not y sub 2, y sub 1. Y sub 1, which is x squared, quantity squared dx. And guys, be careful. This x squared right here does not go into the integration here, does not go into the integrand and divide out with what we have here. No, actually this is just a multiple variable of the integral. So whatever you have outside multiplying with the integral here doesn't go, it's not allowed into the party here. Okay, so what do we do? Minus minus equals to plus equals to x squared integral of e to the integral of positive 3 over x dx, everything divided by x to the fourth dx, right? Okay, so this is equal to x squared times the integral of the e to the integral of 3 over x, that's 3 ln of x. And we're not going to put a plus c here, okay? Everything divided by x to the fourth dx. Okay, well, careful. Again, yes, e and ln are inverses of each other, but we can't do that now unless we move the coefficient as an exponent of the argument by the basketball rule of logarithms. All right. Okay, so this is equal to x squared integral of e to the ln of x squared over x to the fourth dx. Now we may go ahead and e and ln cancels. All right, and this will be equal to x squared integral of x squared over, oh, it's actually not x squared, it's x cubed over x to the fourth dx, and this will be equal to x squared right here, x squared integral of 1 over x dx, which is x squared times the integral of 1 over x dx, which is ln of x. Okay, no plus c here because this is equal to y sub 2. Again, for a higher order differential equation, we write the solution as a linear combination of the two solutions, or three solutions, or more solutions, depending on how many do we have. In this case, since this is a second order differential equation, we will use two terms. That is y equals to some constant c1 y1 plus c2 another constant c2 times a second function c2. y1 is given, y sub 2 we just figured out here. All right, so c1, which we don't know what it is, y sub 1, which is x squared, plus c2 times x squared ln x. Final answer. All right, let's do one more example and wrap up this section. Okay, example number 2. The function y sub 1 equals to e to the 2x is a solution to the differential equation given by y double prime minus 4y prime plus 4y. Find the general solution to the differential equation. That is, we need to write the solution as a linear combination of the two solutions in the fundamental set of solutions. In this case, it's 2 because this is a second order differential equation. All right, well, actually, this differential equation is written in the order we require because the y double prime term is just being multiplied by 1. So all we need to identify, well, y sub 1 is given, e to the 2x, and identify whatever multiplies y prime. That is our p of x, which is negative 4. All right. Well, so how do we get the second solution? Y sub 2, it will be y sub 1 times the integral of e to the negative p dx, everything divided by y sub 1 squared dx, which is y sub 1 substituting e to the 2x, integral of e to the negative, integral of negative 4, careful with signs right here, dx. Everything divided by the first solution that is given, e to the 2x quantity squared dx. Okay, e to the 2x times the integral of e to the integral of 4 dx, simplifying the negatives, e divided by e to the 4x, careful, power of another power multiply the powers 2x times 2, that equals to 4x. Okay, and again, do not cancel these two. This is just a multiple. This does not is not allowed into the integration party inside here. All right, well, so e to the 2x times the integral of e to the 4x divided by e to the 4x, all right? Oops. 4x dx. And in this case, we'll see how these two reduce. These two cancel out. So that equals e to the 2x integral of dx, which is simply e to the 2x times x, which I'd rather have this as x e to the 2x. All right, so that is our second solution, y sub 2. Now let's write the general solution to the differential equation as a linear combination of the two individual solutions. That is some constant 1 times y1, which was given, plus another constant c2 times y sub 2, which is the one that we just found. All right, okay, that'll be equal to c1 y sub 1, which is e to the 2x, plus c2 x e to the 2x. All right, and that is the solution to the differential equation. All right, actually, just to give you the heads up of what we're going to do in the next section, we're going to solve this equation. I'm not sure if it's the same numbers, but actually the same type of equation with a way quicker method rather than going through this huge and humongous formula to find the second solution by reduction of order. Well, we'll get to see that in the next section. For now, we're done with this section.